So I am an absolute fan of your country and your people, and I feel great to be here. It's the second time, hopefully not the last. And well, I have prepared some lectures with the following objective in mind. So to try to propose some open problems together with motivation and arguments for studying such things. And there is a common theme of the whole series of lectures, which is the following one. So this is some expectations on special projective manifolds. Okay. And here I have to make one joke because it's unavoidable. So I will define in a moment basic terms, but let me warn you that this word is very subjective, and I don't know how it happens in Korean, but in English it's easy to see, because there is this famous proposition, "Darling, you are so special to me." So this is kind of the most subjective proposition you can think of. So of course this implies that there will be some particular choice here, and I am assuming full responsibility. Professor Kwak is innocent this time, not absolutely innocent, of course. Okay. So the first lecture will be about small codimension. And being of small codimension will be one instance of being special. Okay? There will be some other instances too. Now the common context of everything I will talk about is this. So complex field as base field. Then we shall look at embedded projective manifolds. So X is a manifold, that is to say smooth. It will always be assumed to be reducible and also non-degenerate, meaning not contained in any hyperplane of Pn. This is of course not a restriction, otherwise you can simply take a smaller n. And also I have some, I'm an old guy, so I have some, fixed ideas. So I like to denote the dimension by n, and also the codimension by c. So these two numbers will be very important, because the basic definition we start with is, so small codimension means simply C small or equal to n. Okay? Well, this sometimes, right? So the opposite is right? And now you begin to feel why this is a special situation. Because one of the first theorems you learned, hopefully, in algebraic geometry, is that if you take any projective embedding of a manifold, you can project it isomorphically from some general exterior point to a projective space of this dimension. Right? So this tells you essentially nothing. Right? You can always assume this. Right? On the contrary, if you can go deeper, so to say, if you can project more, then you arrive at this range, which means being of small codimension. And as we shall see, there are some obstructions, some topological, important and famous obstructions to do so. And indeed, the first serious result is a theorem that is due to Barth and Larsen, which tells you that if you look at, say, you can write it with homotopy groups or with homology groups. Let me write homotopy groups. So these natural maps induced by the inclusion are, so this is, I don't know, phi, are isomorphism for indices less than n minus c, and injective okay. So for instance, you see, if you don't have this this condition, there is no conclusion. If you are at the limit, so c equal n, the first case, then here you only get something about pi 0. So you get that such an x is connected. Well, we assumed it to be connected. Actually, you can not assume it and recover the connectedness from this. But what's really serious is what happens next when the codimension is even smaller than n, right? Let me tell, maybe you should look at, in the book by Lazarsfeld. Lazarsfeld book for proofs and a lot of applications, comments, and blah, blah. So that's a very good reference. Let me tell you that a key fact. So first of all, maybe you heard that this is this famous theorem has been precedented by another even more famous one, the so-called Lefschetz theorem on hyperplane sections. Right? This is about comparing the topology or homotopy or homology or whatever of the manifold with the one of the hyperplane section of it. Right? And so if you iterate, you get such comparison results for complete intersections inside some projective variety. And this is usually done by some more theory. But the point here is that in both theorems, so this is an analog of the Lefschetz theorem. But be careful. Here, there is no assumption on X of being a complete intersection. That's why when the result first came, it was looked as a great surprise, and Barth won an invited address for this theorem. But what is essential is the fact that the ambient is a projective space. So you cannot expect such a result for X in some Y. Right? And what is common to both the Lefschetz theorem and the Barth-Larsen theorem is that the main ingredient of the proof, the main fact that yields this theorem is that, so basic fact, it will play a crucial role in what follows, so that's why I like to stress it. So basic fact is this: the normal bundle of X in Pn is M. That's what's crucial. And why is a normal bundle of something inside Pn ample? Well, the normal bundle, by definition, is a quotient of the tangent bundle of the ambient variety. The ambient variety is projective space. And the tangent bundle of the projective space is ample. For instance, from its description by the Euler sequence, right? It's a quotient of a direct sum of ones, and so it is ample. One thing, by way of the first thing I was mentioning, projective space is the only variety having ample tangent bundle. So if you want, this is a miracle, such kind of theorem, that holds for projective space, because any smooth subvariety of projective space has an ample normal bundle. So this is automatic. Okay. Questions? Are you familiar with the concept of ample vector bundle? Maybe for line bundles is okay, right? You are studying Hartshorne book, so I got my information from the Secret Service. So in arbitrary rank, you just mimic the definition from the line bundle case. That is to say, you take the proj of the bundle, and you require that the tautological bundle on the proj be ample, and this one is a line bundle, so you know what it is. Okay? It's a positivity assumption. Good. Please feel free to ask questions if you want to. So 2 corollaries just to see how significant this result is. So assume that, well, that C, if you want, that n is at least C plus 1. Then, from what I just explained, you get something that is rather deep. Any such manifold is simply connected, right? But because projective space is simply connected, so pi 1 vanishes and this map is injected, right? And another corollary, if you go one step further, then working this time in homology instead of homotopy, or better if you dualize and you work in co-homology, and you use also the exponential sequence, right? It is in the appendix to Hartshorne's book, so you should know this too. Then what you get is that in the exponential sequence you control topologically the terms, and there is one H1 of OX star, and this is a Picard group. And by comparing, you get that the Picard group of X is the same as the Picard group of Pn. That is to say, it is cyclic and generated by the class of the hyperplane section. So this is an extremely important information. Z times H, where, as usual, H will be the class of a hyperplane section. So these are 2 significant corollaries of such result. Good. A definition that will come over and over again is the following. So first, let me recall you that X is called Fano if minus Kx is ample. And it is called prime Fano if a Picard group is cyclic, generated by the hyperplane section, as before, and, of course, to be Fano. So, in particular, minus k will be a positive multiple of the hyperplane section. So, this number is positive and is called the index of X. Everything fine? Questions? Good. Can I erase? Yes, I can. I'm not quoting Obama. Is my English bad enough to be well understood? Hopefully, yes. So, we are ready for the first expectation. There will be 10 or 11 expectations. These are problems that I think are true, feasible, that is to say, they will become theorems in the near future, not in the next century, hopefully. And I also believe that if this happens, the world of projective geometry would be more beautiful. So that's why I like to call them expectations and not the used and abused term conjectures that I am not so fond of. Okay. But you know, there is a famous novel, The Great Expectations, by Charles Dickens, that I hate. Anyway, so here is the first expectation. I will attribute the expectations when I am aware of the authors, the first person who expected them. When I'm not, I will leave them anonymous. So, remember, n is a dimension. Now, the first expectation is that there exists a function of n such that whenever the codimension is small and x is not of general type, it follows that the degree of x is at most phi over. So this requires some explanation. This is an extremely sexy expectation. Why? What does it tell? First of all, what means that x is of general type? Then we shall see what means it is not of general type. This would be your job. So general type means that the variety is, in the broadest sense of algebraic geometry, general, meaning that a sufficiently high multiple of the canonical gives a birational map. Right? So you have enough pluricanonical sections to get almost an embedding. That is to say, an embedding on an open subset. Of course, Zariski topology. Okay? So morally, the objective of algebraic geometry is to understand manifolds which are not of general type. Okay? The prototype is for hypersurfaces in Pn, capital N, then everything that's of degree bigger than n plus 1 is of general type. And the rest are the special guys. Here you get Fanos or K3s or, you know, things that are special. And hence, with a very interesting geometry, right? The advantage of objects of general type is that they fit well together. They are friends. They behave friendly with each other. So they form nice families and moduli. The special, meaning not general type objects, are more erratic and varied, and in a sense, although they are a minority, they are very active. Like in politics, you know, in the parliament there is a small group, but they make a lot of noise. Good. Questions? So, what's the meaning of this? The meaning is, so first of all, if you don't have this, right, such a result is impossible. Why? Simple. Take the simplest variety, projective space. Embed it somehow. You know, the embeddings are the Veronese embeddings of a certain index. Okay, embed it somehow. Then compose with some other Veronese embedding of the ambient projective space, and go to a huge projective space with a huge degree. Then project to P2n plus 1, right? Then you will have the same damped variety, which is the most special of all existing ones. It's just a damped projective space, right? But with a degree which is as large as you want, okay? So clearly, if you want to have such boundedness phenomenon, even for special varieties, right, you have to impose that these projections should be excluded somehow, or very rare at least. So that's why this belongs to the subject of small codimension, okay? Now what's the statement? Well, when this codimension is small, manifolds not of general type are finitely many. In what sense? Not finitely many as individuals, but as families. Because the expectation tells you that their degree should be bounded once the dimension is fixed. And you know, if you fix the degree, you have finitely many families. This is Hilbert scheme or Chow scheme or whatever you studied already. Okay? As a conclusion, if there are finitely many families, you may expect to classify them. Otherwise, boop. So, now, let us look at some concrete cases. So, as any expectation, it is based on some theorems. Where are the theorems? Here they come. So, true if 1. Famous paper n equals c equal 2, meaning surfaces in P4. This is the first non-trivial case, because otherwise you have curves in the plane. But curves in the plane are hypersurfaces. For hypersurfaces, I already told you that being special means being of degree at most, well, you know, 3, right? Starting with degree 4, the curves are of general type. So, plane curves. So this is a famous paper in Inventiones by Ellingsrud and Pesky. Another fan of Geist, and or vice versa, whatever. Good. So next, also codimension 2, but n equals 3. This is 3/4 in P5. This was proved by using similar techniques, which are quite refined and sophisticated, by 4 guys. So the abbreviation is splendid, so it's this. So this is Brown, Ottaviani, Schneider, and Schreier. I repeat, same techniques, but very involved. 50 pages. Then, the case n at least c plus 2 was solved by Schneider. So, if you look at this implies that the expectation is okay in codimension 2. Right? Because you can have n2, L super 3, boss, or bigger or equal 4, but bigger or equal 4 means bigger or equal c plus 2. Okay? So it's a theorem in, I'm not preoccupied about giving an optimal bound or whatsoever. Existence is all I'm interested in. And then, that's, to the best of my knowledge, the latest contribution, together with Thomas, we took Schneider's idea, one of Schneider's idea, and proved that it is okay if X is Fano or arithmetically Cohen-Macaulay. And this is myself with my friend Thomas Matei from Nancy. Another Romanian working in France. Hey, hey, hey. I'm telling this for you. Okay? So, I don't know if arithmetically Cohen-Macaulay is something you know. You should, because the boss, not that boss, this boss, is working on this, so you should know. Let me tell you that there are, well, there is an algebraic definition that you take the projecting cone and you localize at the vertex, and this ring should be Cohen-Macaulay. If you know what this means. If you don't, you lost nothing. That's the last visit here. And there is a geometrical description. The geometrical description is the Serre map is a bijection. You know, it is a bijection for indices sufficiently high, right? So in classical terms, the linear system cut out by hypersurfaces of a certain degree is complete, okay? But for any degree. For large enough degree, this is Serre's theorem, right? It's in Hartog. And moreover, the cohomology groups of all OXNs, I mean all invertible sheaves that are restriction to X from Pn, are 0 where it should. I mean for I, the index of the cohomology group, between 0 and dimension, strictly positive, strictly less the dimension. So the two conditions combined are equivalent with the fact that local ring of the vertex of the projective cone is Cohen-Macaulay. So this is how you should connect them. Good. Now, I would like to present you a proof of this last part, because I think it is quite instructive. Okay? So I'll prove this. The proof is completely different from the first two things, which are very much specific to codimension 2. They are very subtle and, well. However, this, I think, if somebody will have a chance to prove this, of course, codimension 2 is already a theorem, right? So this technique here are not appropriate. Good. So, so let us denote by this a degree, x. And of course K is canonical, and H is the hyperplane section, right? So I will play with these divisors and fix some A, which may depend on the dimension only. Okay? It's an integer. Actually, you can suppose it's non-negative. Now, the first thing that you use is the so-called self-intersection formula. The self-intersection formula is an important theorem about Chern classes that was conjectured by Grothendieck and proved by Lascu, Mumford, and Scott in a famous paper. In our case, it tells us that the last Chern class, so of the normal bundle, so maybe I will abbreviate to write less. So I consider the normal bundle of X in Pn. So this is a vector bundle of rank C, the codimension, right? Okay, but for the moment I write it instead of C because I don't like to see C, index C. You will tell me some ugly words. So for the moment I write N, capital N minus, okay, of the normal bundle equals D times the intersection here taken N minus N times as a cycle. So this is a cycle, this is a cycle, right? So this is an equality in the Chow ring of X, right? Now in our case, so we may assume capital N is 2n, right? Because this is obviously the most interesting case, the last case. And if I give up the hypothesis that X be non-degenerate, I can always assume this, right? So remember that small codimension was this, right? Okay, so if I prove things here, it's enough by possibly giving up the variety to be non-degenerate. So this is, so here, N minus N is N, right? So this is again the degree. It's a self-intersection of the hyperintersection. That's a degree by definition. So this is D squared. So this is the famous double point formula, right? The square of the degree is just the last Chern class of the normal bundle, which is a number because it's the last Chern class, right? It's a zero cycle, but you, by abuse, you take its degree. Okay? So this is the first ingredient. And now we are going to apply some deep result by Fulton-Razarsfeld. And this was Schneider's idea. That we borrowed from him. This is a famous paper in Annals, in which the two authors proved that if you have a vector bundle, which is ample, there are some universal expressions. I don't know if you ever heard about Schur polynomials. This is something related to representation theory. I don't want to enter into this because it's another subject, and it is not mine. And the point is that these are some God-given polynomials that have some very nice combinatorial and blah, blah. They appear in many situations. Now, the theorem by Fulton-Razarsfeld is the following. If you have an ample vector bundle, and you consider the values of these Schur polynomials in the Chern classes of the vector bundle, the result is positive. Well, the result in general is a cycle. But you know what the cycle being positive means, right? It's a positive cycle. Okay? So that's a theorem. So positivity of Schur polynomials on Chern classes of ample vector bundles. Actually, I only need a special case because one of these Schur polynomials is this one, ck minus 1 times c1 minus ck. This is one such. So think of these as Chern classes. And you see, they have to be homogeneous to give you a cycle of pure codimension, right? So what I know is that if you apply this to the normal bundle, you get something positive, okay? Because, once again, the normal bundle of any subvariety of projective space is positive, because it is a quotient of the tangent bundle of Pn, and the tangent bundle of Pn is positive, is ample. Sometimes I say positive instead of ample, it's the same. The definition is U1 again. Okay, but this thing can be iterated, right? By giving, so you take K first to be the last, so the last, and then you iterate. So this will eventually lead to the following. So d squared, which was the last, now I replace n, capital N minus n with n, because they are equal. And sorry for this capital N and this capital N, of course they have different meaning, but you are intelligent people, no doubt. And this will be smaller by iterating, tick, 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 tick. What is the final result? It will be the nth power of C1, right? So the final result will be C1 of n at the power n, right? C1 of n is a line bundle. And this is its nth intersection, the self-intersection. Okay? We are on X, which is n-dimensional, so everything fits. Good. Now, who's this guy? So C1 of n is easy to compute. The result is what is called a junction formula. Because you have this obvious sequence that defines the normal bundle, right? And you take determinants, okay? And as a result, you get this thing. So here, the tangent bundle of Pn, you know. So this is 2n plus 1 times h. That's the result. This is actually capital N plus 1. But capital N is 2 times smaller. So, let me conclude with this important thing that I will keep here. We proved that this, the square of the degree, is always, so far, no hypothesis, right? No hypothesis. This k plus, this is an adjoint, k plus 2n plus 1h power n. Okay? Okay, now what can we do? Many things. First, erase. Then, so remember, my goal is to prove the statement in 2 cases, Fano and arithmetically Cohen-Macaulay. Okay? Okay. Now, I fixed this A, and I did nothing with it till now. Now comes into play. So assume that this intersection, k times hyperpersection n minus 1, is at most A times D. Assume this. So let me repeat, A can be anything, but it has to depend only on n, not on other parameters of the problem. Good. And now I shall do some ballet in order to find out that the degree is bounded. And this is really, I think, quite nice. And let me remind you the following. So you have met certainly the Hodge index theorem, say for surfaces, right? Hodge index theorem, one of the fundamental inequalities in algebraic geometry, okay? It can be generalized by a kind of obvious induction, reducing it to the surface case, where it is proved in Hartson, for instance. In the following more sophisticated and very general way. So, Hodge index theorem, sophisticated form. This is the following. So if D is nef, I will explain in a moment, and H is ample, then you have the following: H j plus 1 times D n minus j minus 1 times H. Now you put vice versa, j minus 1 D n minus j plus 1, okay, is at most H j D n minus j squared. Now this is, you can recognize, of course, it's a kind of generalization. This is easy to see. And this thing, nef means that the intersection with any curve is non-negative. That's a good numerical properties, weaker than ampliness, right? Okay, so an F divisor, these are divisors. An F divisor is a divisor intersecting any curve non-negatively. Okay? Okay? And from this thing, that is, I leave you as an exercise to prove these things. So this implies, so exercise, some induction, the following inequality: D to the n with the same hypothesis, fraction H n minus 1 times D at the power n, and here H to the power n at the power n minus 1. So this is some, these are tricks, sorry guys, but that's life. You have to do tricks sometimes. Now I'm going to apply this with the following choices. So now take, so H has to be ample. It will be the hyperplane section. So here H is H, right? So when I apply this, I take as the ample divisor will be the hyperplane section. It is very ample, so ample in particular, right? No mystery here. What I have to explain is the D. D will be this guy, the determinant of the normal one. So this guy is K plus 2n plus 1 H. And I claim that this is also ample. So if you have problems with this nefness and blah blah, and you never saw nefness till now, forget. Write ample, which is stronger but enough for our purposes. I just gave you the more general result because it may be useful sometimes. Why is this ample? This is ample because of the following exercise that students are kindly invited to do. Namely, prove that K plus n plus 1 H is globally generated. Meaning the complete linear system has no base points. Hint, use induction on n, standard exact sequences, Kodaira vanishing, and reduce to the classical case of curves, which you should know because it follows from Riemann law. So you cut with hyperplanes until you get a curve. For curves is true, and the result lifts, so to say, because an H1 vanishes, and so you can lift section. Standard thing. So this is an exercise, induction on N. Okay? Okay. So now this is the first exercise. First exercise, if you have a second exercise, if you have a globally generated and you add some very ample, you get something very ample, because you can separate points and tangent vectors in an obvious way, right? So this implies that K plus, look here I have 2n plus 1, so I'm adding an n times something very ample. So this guy is even very ample. So in particular, it is ample, right? So this is very easy in our case. Okay? If you want to be smarter, only if you want, you can think about the following problem. If, say, H is ample, forget about very ample. Does this imply that K plus n plus 1 H is also, well, ample is too much. Nef? And here, this is very interesting for some people, myself included, because this is true, and this fact is equivalent to Morricone theorem. So this is true, but hard. Equivalent to Morricone theorem. This is a nice remark, I think. So either you know something about Morricone theorem and the Cone theorem and blah blah, or you don't. If you don't, obviously forget about this. Sorry, I just mentioned it because you see this difference here. For very ample, it is an exercise in first year of algebraic geometry, not of kindergarten. Here it is much deeper, but still true. So this may be of use for somebody trying to generalize this. Okay, so this thing applies. Agreed? Maybe we should switch a little bit because some people are already sleeping. I'm not included. Okay, so okay, thank you. So let us see the result. Thanks a lot. So you see, I'm just replacing D by that fellow.
But you haven't yet defined.
No. I did nothing for the moment. I'm just preparing. It's not in 2 words. I mean, you have to. So I start from here. So I know that D squared is smaller. This is the part I know. K plus 2 times n plus 1. H power n, right? And now I continue with this one, right? So this is smaller equal what? Well, h to the power n minus 1 times k plus 2n plus 1 h, right? Everything at the power n. It's terrible, but that's life. And this is d to the power n minus 1. You will see that the final result is kind of unexpected. Okay? Okay? Now time has come to use this. So this will be smaller equal, according to what's written there, to what? So you see there is so let me write first with equal, because otherwise some people will have difficulty. So h n minus 1k, I write it vice versa because that's better, plus 2n plus 1 times what? h n minus 1 h, this is the degree, right? Everything at the power n. It looks horrible. It looks something, what are you doing? Wait, d n minus 1, right? And now, this is smaller equal. So you see, this part, this is a number, right? Is smaller equal a times d. So everything is positive, so I can do. So d will be a factor. So what I get here is a plus 2n plus 1 at the power n, right? And a d, so a d at the power n, right? And here I have a d to the power n minus 1. Okay? So I do that. And here I have d squared, so this d goes. So the final thing is d smaller, a plus 2n plus 1 n. That's the boundedness I wanted, right? Now, see, Joe. Fano, take A to be 0, because if this is negative, this will be negative, right? So you take, so Fano case already. Fano, take A equals 0, and you get a nice bound. It is double exponential. Don't ask me for a linear bound or something. 2n plus 1 power n. So this bounds the degree of any Fano manifold that is embedded with small codimension. And I think it's a nice enough formula, so to say. Okay. Now, why bother with this? Why not putting 0 from the very beginning? Because I need this for the other case, for the arithmetically Cohen-Macaulay. And here I will prove something that is quite interesting, and I'm sure that the boss will be the last to get asleep because he likes this. We shall see that we can prove boundedness if we can prove boundedness for what is called the Castelnuovo-Mumford regularity. Look at his eyes. He's already. So the point is that now, okay, so I explained the Fano case. Okay, now I have to explain the other case. Introduction. I will prove more than boundedness holds for arithmetically Cohen-Macaulay. I will prove the following: that, you know, there is this theorem A, theorem B, Cartan-Serre asymptotic vanishing, right? Right? If you have a fixed sheaf, coherent sheaf on Pn, blah, 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 and if you twist it with something sufficiently high, then you kill all cohomology in positive degrees, right? Cartan-Serre. The point is that the number at which the cohomology starts to vanish depends on the sheaf. It's not a universal bound. Now what I claim is the following. Consider a class of varieties such that for the most natural sheaves, the rank 1 sheaves, the invertible sheaves induced from Pn, that is for OX case, right? There is no intermediate cohomology for a sufficiently large K. So consider all varieties, so fix a K, but look at it as a constant. And consider all varieties such that their intermediate cohomology for these sheaves vanishes starting with K. This gives a stratification. And you are in small codimension. Then this forms a bounded family. So all these have bounded degree. Now arithmetically Cohen-Macaulay, this is 0 all over. So here you can take any bound, right? It's the easiest case. So this is one condition which ensures boundedness. But the good news is that this is equivalent to the boundedness, because conversely, admit that it is bounded. If it is bounded, if the family is bounded, there are finitely many degrees. And it is known from Castelnuovo-Mumford theory that such a bound only depends on the degree. So if you have finitely many degrees, there will be one constant good for all. You understand? So the proof shows, actually, that to get boundedness of the degree is equivalent to getting boundedness for this vanishing of cohomology, a uniform vanishing for all of them, right? So it's not trivial. I have to prove this, and I will need this will be the bound, actually, which may depend on the dimension, but not on anything else. And the flavor of the argument is, this is our contribution. The flavor of the argument is very typical of regularity, as we shall see in a moment. Okay, was it clear what I want to do now? Okay, so the arithmetical Economacaulay case will be just trivial because any bound will work. Okay, so yeah, what to erase here?